Welcome. This is Chuck Ridgway, the Automation Technology Manager here at Horner, and thank you for joining us for another live stream on Tuesday. So for the last couple of weeks, we've been talking about CAN-based networking, and specifically talking about a proprietary network that Horner invented that has some really nice features. Well, this week we're going to stick with the theme of CAN-based networking, but we're going to talk about a different network. This week it's all about CANopen networking, and specifically for this week, how it works. And joining me again today is Mr. Casey Gardner. How's it going today, Casey?
Hey, not too bad. How's it going, Chuck?
It's going well. Now, all of us have a lot of experience with CScan. You know, we've added IOTA systems, we've had OCSs talking peer-to-peer to each other, but CANopen is something that we have less experience with. I'm guessing that's the case for you as well.
Yeah, it's definitely quite a bit less common. I think it's been probably about 4 years since I last messed with an application with it, so it's been a while for sure.
There are some really interesting use cases, though, some situations where it makes a lot of sense. You know, CScan is a proprietary network, so in that scenario, you're never going to be adding third-party devices to a CScan network. So if you have a requirement for a third-party device, there's a pretty good chance CANopen might be a good option. Also, CANopen is a terrific network for adding motion control type devices as well. So we've got lots of great use cases. We're going to go through some of those today. And while I do that, Casey is going to be manning the chat, answering any questions that you have during the broadcast, and then he'll be joining me at the end to figure out, what I screwed up. All right, let's go ahead and get started. So let's take a look at an outline of our talk today. So again, what we're talking about is CANopen, which is a field bus-based network as opposed to a proprietary network, which is what CScan is, and we've covered that the last couple of weeks. But here's what we're going to cover this week. So we're going to do a quick review on the CAN chipset. So both CScan as well as CANopen are based on the same chipset. It's the CAN chipset. Now we'll do a quick review there, so if you've missed our previous couple of weeks, you'll still be able to keep up. What is CANopen? That is going to be the next question we're going to answer. Why use CANopen with an OCS? What's the benefit? Why would you want to do that? We're going to dive a little bit into CANopen messaging, actually quite a bit. Now we're not going to get down in the weeds, if you will. What we're going to try and do is talk about some of the different messaging types. They're really kind of called protocols in CANopen nomenclature, but we're going to talk about some of the different messaging types for CANopen. And there really are some very clever messaging types that offer some unique advantages compared with other field buses, whether they're CAN-based or otherwise. So it's definitely worth covering for sure. And then we're also going to, at least briefly, I'm going to show you how to select CANopen if you're using a Horner OCS. How can I select CANopen as my communication option or a communication option in my application? And then next week, just like I did with CScan, where we had a 2-week series, next week it's all going to be about hands-on. So we're actually going to go in and configure devices. We're going to get a couple of CANopen third-party devices talking to Horner OCS. We're going to talk in detail about the use case and the applications. So this week is a little bit more of how things work. Next week is all about the hands-on. Okay, let's start with that CAN bus review or CAN chip review. So what is CAN? So CAN stands for Controller Area Network. It's a peer-to-peer based communications network. It's based on a standard chipset. So any CAN-based network is using effectively the same set of chips or a microcontroller or microprocessor with that CAN capability or CAN chip built right in. Okay, and what it does is it allows a variety of different devices to communicate with each other, whether it's in a factory or otherwise. From an application standpoint, it really thrives in harsh environments. When we say harsh, we're talking about noisy environments electrically, we're talking about tough environments environmentally, and therefore it's used extensively in vehicle applications as well as industrial applications. So as part of an introduction to CAN, let's quickly revisit a comparison between CAN and Ethernet, because in the industrial world, we're all very familiar with Ethernet these days. So CAN was designed for safe data exchange in harsh environments, while Ethernet was really designed to transport massive amounts of data in a reasonable time frame. Now, both of these devices have huge economies of scale with billions and billions of chips and devices sold every year which support either CAN or Ethernet or both. If you take a look at the strengths and the weaknesses of the two different communications options here, you'll see they complement each other very well. With Ethernet, huge bandwidth, support for dozens of protocols, everything from sending email to browsing websites, etc., etc. However, there are downsides. It does take a fairly large code footprint. You need a fair amount of source code in order to utilize Ethernet. And Ethernet also struggles with collisions and data integrity. So it's not the strength of Ethernet for sure. Whereas if you take a look at CAN, its downsides are limited bandwidth and support for much, much less or much fewer protocols. However, it's got a very small code footprint, so it can fit in even a tiny microprocessor. It has excellent data integrity, so very little data is ever wasted, lost, or just not available. And also, its collision handling is tremendous. So with Ethernet, when you get up to about 50% collisions, or 50% bandwidth utilization, I should say, your collisions start becoming a real problem and you start losing a lot of bandwidth. Now, Ethernet's a huge pipe, don't get me wrong. Now, CAN, which is a much more limited pipe, when you get up to 80 or 90% of bandwidth utilization, it still works really well because when there are collisions, a message always gets through. You just don't have lost data with CAN. So again, CAN and Ethernet complement each other very well. So that's your quick review of CAN. Now let's dive into what is CANopen. All right, last 2 weeks we talked about CScan, which is a protocol based on the CAN chipset that was invented by Horner. This week and next week it's all about CANopen. So CANopen is a standard communications network based on the CAN chip, of course, and it's most popular in factory automation. And it was developed with motion control applications in mind. So that's one of the things that makes it unique when compared with other field bus protocols. A lot of other field bus protocols were kind of based on, interfacing sensors, for instance, and actuators, not necessarily with motion control in mind. And CANopen was, which is a big advantage to it. But it's not limited to motion control. And then like a lot of open field buses, it does have a organization that administers it, and in this case it's the CAN in Automation, or CIA Automation. But it's not that CIA, if you get my drift. Okay, so I thought it would be a good idea just to compare CANopen and CScan. They're both CAN-based networks. Let's compare them. So CANopen is a standards-based network, so designed for interoperability. So having multiple devices from multiple manufacturers all talking to each other and being integrated in the same application. It was also designed for motion control, so it works very well whether it's single axis or multi-axis motion control. What was CScan designed for? Well, if you were with us the last couple of weeks, you'll probably remember that it's a Horner designed network. It was designed for efficient data exchange and for easy I/O expansion with good performance. So really two completely different design goals with those two protocols. To further compare, CANopen definitely includes support for a fair amount of peer-to-peer messaging, but it also has a lot of elements built in of master-slave and client-server. So depending on which messaging service you're using, it really acts differently. Okay, and CANopen is highly complex, no question about it. Can't beat around the bushes there. It's got some great capabilities, but it's not simple. With CScan, it's almost a purely peer-to-peer type message structure, except for output devices like I/O relay modules or analog output modules. Other than that, it's pretty much purely peer-to-peer. It's really easy to use and it's much simpler. Now, why would you use CANopen with OCS? When you have CScan, which is a nice simple network to add I/O, why in the world would you use CANopen? Well, okay, let's say we do need interoperability. We need the ability to interface with a third-party device over a network and not just wired up via I/O. That's not available on CScan. CANopen supports that very well. Let's say we've got a motion control application, even if it's a simple one, maybe just a stepper drive or two. We can always use step and direction with devices like Horner OCS and small PLCs, but you can do a heck of a lot more capabilities with a CANopen network connection to a stepper drive or two than you can with step and direction. So that's definitely a compelling reason right there. Another one could be the ability to add multiple encoders that are all synchronized with each other over a network. That's pretty cool. So there are use cases for sure, but it's not just anytime you add I/O, you're going to want to use CANopen. It's not that sort of use case, which you do get with CScan. And again, the reason why you wouldn't use CANopen everywhere is because it's just not that easy to use. I don't want you to get too intimidated here. Again, one of the goals of this session today was to try and take some of the, the mystery out of CANopen. But it is a highly complex protocol for sure. So if you're just adding I/O or doing peer-to-peer communications between OCS units, certainly use CScan. It's much easier and mostly plug and play. But use CANopen when you can take advantages of its strengths of interoperability and motion control. All right, let's talk about which Horner products can utilize CANopen. Now, CANopen is not supported in our lowest end products. Our entry-level series, the Micro Series OCS, the X2s, the X4s, the X7s, the X10s, they don't support CANopen. You first get CANopen support really in the XLE and XLT. And if you're looking for instance, a CANopen slave, then an XLE or XLT might be a great choice. If you're looking for an XLE, XLT, if you're looking for a CANopen master, then one of our other products would probably be a better choice. Can you use CANopen master with XLE and XLT? Absolutely you can. But you're going to probably, in most applications, motion control or whatever, other applications, you're going to be better off with one of our other products, such as our X5, our XL4, EXL6, or EXLW. Those are perfectly capable CANopen masters. They certainly can be, and they feature a single CAN port. Now, if you want to take it to the next level in terms of flexibility, you can go with our XL7, EXL10, or XL Plus. Those products have 2 CAN ports, and CANopen is available standard on CAN 2. So you can mix and match CScan for I/O on CAN 1, and you can add CANopen on the second CAN port for things like motion control, etc. And then what happens if you have an application, let's say, where you need to add a couple stepper axes over CANopen, and you still need expansion I/O. You can't have CScan and CANopen talking on the same CAN port. Well, we've got that covered as well. We offer for SmartRail a CANopen base that allows you to have expansion I/O via SmartRail along with those third-party CANopen devices all sitting on the same network. And the beauty of it is we have made the SmartRail configuration really easy. Now, to kind of take it to the next level, all right, these products support CANopen. How do I get it? How do I order it? How do I acquire it? With the XLE and XLT, as well as the single port XL series products, it's a field firmware update that you would download for free. So you go to our website, you go to our firmware download page, and you'll find we have, for some products, or for all the products that support CANopen, you have your choice between the CScan firmware or the CANopen firmware. Now, if you're using a dual CAN port model, like an XL7, EXL10, or XL Plus, then the standard firmware supports CANopen selectable on the second CAN port. And then with SmartRail, if you need a CANopen support on SmartRail, you just order the CANopen version of SmartRail from the factory through the part number. All right, now we're going to dive into kind of the architecture as well as some of the messaging that's available on CANopen. Now, my goal for today is to help with your understanding without going so far into the weeds that I lose you and make you intimidated and not want to use the protocol, because it's a really good protocol. And I highly recommend it for those use cases where it makes sense in your application. All right, so let's start with what is a CANopen device. All right, now what we're talking about here is a generic CANopen device. It could be a CANopen master like a XL4 or an XL7. It could be a CANopen encoder, which acts as a slave, for instance. It could be a drive, a variable frequency drive, or a servo drive. Could be a whole number of things. Those are all CANopen devices. And any device hanging off CANopen is going to have kind of 3 things that it's made up of. And let's start at the top. So it's going to have application code running on it, right? And that is what makes it do what it does. If it's a servo drive or a stepper drive, it's going to handle the motion control. If it's an I/O block, it's going to handle the inputs and the outputs. If it's an OCS, it's going to control the application. Now let's skip to the bottom level which is the CANopen protocol stack. So these devices, whether they're servos or steppers or OCSs, they need to be able to talk over CANopen, so they need to know how to do that, and a CANopen protocol stack takes care of the messaging. Now, how does the application side talk to the networking side? Well, that's done through what's called an object dictionary. That's the link in the middle there, the middle part of the sandwich. So that acts as the glue between the application side and the CANopen communication side. Let's talk a little bit more about that object dictionary. Okay, so the object dictionary, the way that it kind of links the application and the network is it provides a list of a reference list or an index of all the information that can be exchanged between the application and the network. Okay, and that's all available in one place, and it's pretty extensive. Now, it just so happens that it utilizes hex-based addresses instead of decimal-based addresses, so you have to kind of, dust off your hex-based conversion skills or calculator or web page, whatever you use for that. But that just adds an extra step, if you will. And another thing that's part of the object dictionary, which is very handy, is that CANopen supports what are called device-specific profiles. So if you're integrating a variable frequency drive or a stepper drive or an encoder, there's a standard profile or a standard, list of parameters for that sort of device in CANopen. That's called a device profile. Really handy, because if you've got drives between different manufacturers, they're gonna basically have a memory map that looks almost identical. Now, it's not completely identical because CANopen also supports manufacturer-specific areas as well. So if a manufacturer wants to do something special or something extra, they can do that. They have an area of memory that they can dedicate to that. So that's the CANopen Object Dictionary. Again, the glue between the application side, what does the device do, and the networking side. And as I just alluded to, CANopen device profiles are one of the powerful features of CANopen, and I just put a handful of them here on the screen. Everything from encoders to pumps to RFID devices to energy management devices like energy meters, those sorts of things, to motion controllers, variable frequency drives. There's quite a few profiles available, and that's a very useful thing. It's definitely a valid attempt to standardize how similar devices from different manufacturers communicate on the network. Okay, so next I'm going to dive into some of the CANopen messaging types. Now, in the official parlance of CANopen, these are called protocols. Normally when we're talking a protocol, we're talking an overall protocol. But these really are different messaging types, but they're technically called protocols. So we're going to dive into these different message types, tell you what they do, why they're useful, why they're not useful, because some of them aren't all that useful, frankly, and hopefully, again, take some of the mystery out of these things and also highlight some of the really clever things, some of the clever messaging that CANopen does. Okay, let's start with the SDO protocol. SDO stands for Service Data Object. These are messages that are sent on an occasional basis, all right? And you can use an SDO type message to access any data that's in that CANopen dictionary, what I talked about a couple slides ago. So any piece of data that's in that dictionary, it's accessible from an SDO. And you're typically going to, again, use an SDO only in a scenario where you're going to need that data occasionally. Not on a high-speed basis, not on a continuous basis, occasionally. Now, in the case of the SDO protocol, it operates kind of like master-slave. Technically, it's client-server, but it's really a master-slave type architecture. Okay, the master device is effectively going to request the data from the slave. Now, you can have slaves requesting data from other slaves. That's definitely possible, but most slaves aren't all that configurable where you can actually have them retrieve SDO information. So typically what you're going to have in that scenario is an OCS acting as a master, doing an SDO read or an SDO write to access a parameter within a slave device, read-wise or write-wise. Okay, so that's the SDO protocol. That's good for occasional use. Now the PDO protocol, that's called the process data object. That's your runtime data. Okay, that's for high priority control and status information. It stands for process data, or what's happening at runtime. Okay, Now, most slave devices, as well as master devices for that matter, have both transmit PDOs and receive PDOs. So this is kind of one-way information. PDO type data is either transmitted by a device or it's received by a device. So it's not like Modbus where you have like one set of registers where you're reading and writing them with multiple devices. With the PDOs, you're typically having one device transmitting them and another device receiving them. Now, some slave devices have what's called a static PDO map. In other words, the manufacturer has determined this is the process data that's important in every application. Therefore, this is the data we're going to make available at runtime for your access. So a really, really simple CANopen slave might work that way. However, what you'll find is most CANopen slaves offer what's called variable or dynamic type mapping. So as an applications engineer, you may be able to utilize the default data map for the PDO for that device, but you'll also probably have the ability to specify some additional data that is important in your application that may not be important in somebody else's application. So that's a really powerful capability in CANopen as well. So not only can you have access to any data you want, like with an SDO, you can configure it into a PDO and get it quickly and regularly. Very cool. Okay. Now, one other thing that's nice is that, like a lot of field buses, most slave devices are provided with what's called an EDS file, or an electronic data sheet. So that means that when you're selecting the PDO data that you want to read and write from that slave device that has dynamic mapping, you can just pick that parameter off a list. You don't necessarily have to just type in its reference number or its address. You can go through a list and say, I want that information, I want that information, and you're picking out the status word or the current position or the destination position, whatever the case may be. So that's another real nice capability. You don't have to just type in addresses. Okay, now let's talk about how PDOs are triggered. We talked about the fact that PDO stands for process data, and it's data that's sent out at runtime. Okay. Now, another nice thing about the way PDOs can work is you have flexibility in terms of how that or when that PDO data gets transmitted. Okay. Now, you have event-driven triggers that you can configure, and in that scenario, the producer, which is typically, let's say, the slave, it can determine when to send the data. Okay, so it might just send it on a change, it might send it every 50 milliseconds, but that's strictly up to the slave to determine that. So that would be an event-driven type trigger for a PDO, which is very handy, and you can configure that trigger most of the time. Now, another capability or another triggering type event for a PDO is what's called a sync-driven or cyclic type transmission. So in that scenario, there's a special synchronization message that the master can send out that the slave can respond to in a synchronous manner. That's one of the most awesome parts of CANopen, and I'll talk about that in more detail later. But the ability for slaves to react synchronously to the master is one of the things that makes CANopen really good for motion control. And then you have acyclic type sync-driven triggering, which is similar except that the transmission by the slave is based, even though it's partially based on the sync message that it receives from the master, it's not as tightly coupled to that sync message as it is in a cyclic application. It's not fully synchronized, if you will. And then there's kind of an old-fashioned type approach where the actual producer doesn't really determine when to send out the PDO message. It's not the slave that sends it out or determines when to send it out, but it's actually the master that sends an RTR message, a special message, and says, hey, can you give me this information? So in that way, it's transactional, kind of like an SDO, except it's being done in the PDO type time frame. But that's a pretty old-fashioned approach that I don't see used all that often, frankly. The big ones are the event-driven and the sync-driven type triggers. Okay, so we've talked about two different message types so far. SDOs for occasional access, they're like a master-slave type scenario, and PDOs, which is runtime data, where you have the ability to specify what data you want available at runtime and when it's transmitted, whether it's synchronously or whether it's asynchronously. Now let's talk about some other elements of CANopen. One is being network management. So all CANopen devices have to support the network management state machine, and that's that diagram you see over there to the right. And in that state machine, you'll see 4 different states, and we'll go through those in a second. But it really defines the communication behavior of the CANopen device when the device is in that state. Now, what are those states all about? Well, let's talk about that on the next slide. And that is, I guess we got to wait another slide yet to talk about that. Let's talk about how the devices get in that state. Now, let's not necessarily what that state means. So, again, going back one slide, this state machine defines what state all the devices on CANopen are in. Okay, specifically the slaves, because they're the ones that need to be controlled. Now, how do those devices get switched into different states? Well, something called the NMT protocol, which happens in the background, that's what changes states. So the CANopen master, which in our case is almost always an OCS, it is in control of putting slaves into a specific state. All right, and that can be done with a function block from ladder, or more commonly, it can be done in configuration where you just say, hey, put everybody into operational mode, when the system starts up. Okay, so there is a special protocol in the background which allows the master to control the state of any particular slave. Now, what do those individual states mean? Now we'll talk about that. Okay, we have the initialization state, which basically is what the device will automatically enter into after a reset or a power up. Okay, so I'm a slave, I power up, I automatically come into the initialization state. Next, it can go into the pre-operational state. What that means is it's gotten through its initialization process, and this is all handled by the slave, and it can just go right into pre-operational state. In that scenario, or in this case, it has some capability to talk on CANopen. Namely, it has the ability to respond to SDOs and some other type messages, but it can't handle PDOs at this state. Just SDOs, just occasional messaging and some other messaging. No process data, no runtime data at this stage. Now, when it goes into the operational state, and the master is going to put it there, typically, at this stage, it can execute all CANopen message types, including the runtime PDOs. All right? And then if something goes wrong, or the master stops the network, if you will, then the device can go into the stop state, but in the stop state, it can only respond to an instruction to go into a different state through an NMT command. So you can't send SDOs to a slave and have it respond if it's in stop mode. You're going to have to, as the master, you're going to have to make sure it's at least in the pre-operational mode if you want to exchange any messages with it at all. Okay? All right, so that is, other than network management messages, that is. So that is all about network management. It's a standard state machine. Devices have 4 different states they can be in. The master controls when the devices are put in that state. It's usually just as easy as checking a checkbox. And when you're in the pre-operational state, you can do most things, but not PDOs. When you're operational state, you can do everything, including PDOs. Okay, now let's talk about another useful protocol in CANopen, very similar actually to what we have in CSCAN. For those of you who attended our CSCAN session, you may have noticed or remember that we talked about heartbeat messages. We have the ability in CSCAN from logic to send and receive heartbeats so that we can ensure that our device is healthy, and we can broadcast that fact to other devices that are paying attention to our data. Works almost exactly the same in CANopen. So it's a simple protocol, doesn't take up a lot of bandwidth. You can configure devices to generate a heartbeat on a periodic basis. Typical might be 500 milliseconds or 100 milliseconds. Okay, devices also have the ability to monitor the heartbeat to make sure another key device is available. If that other key device is not available, for instance, that intelligent slave could decide to take some sort of local action. Or an intelligent master, almost all masters are intelligent, could decide to take some other action in the case of a slave going away. Now, there's another there's another error control protocol that's out there called node guarding There's nothing wrong with it per se, but it's pretty old-fashioned. So if you have your choice between an error control protocol, just use the heartbeat. You don't need to use the node guarding. It's pretty much outdated. All right, now this is without doubt my favorite capability of CANopen. And it's one that I touched on earlier in the presentation, and that's the ability of a CANopen system to be synchronized between the master and slave, or at least certain messages can be synchronized. So this is accomplished through what's called the sync messaging. Okay, a sync producer, which is almost always the master. Okay, and it's always an OCS in our systems that we're supporting. Okay, so the Horner master can be configured to generate what's called a sync pulse. And you can configure how often that sync pulse gets sent to the network. All right? You know, it could be every 50 milliseconds, it could be every 10 milliseconds, it's pretty much up to you. And that sync pulse gets sent out in a periodic basis, again, let's say every 20 milliseconds or whatever it's configured for. And it's a highly effective tool to allow all the devices on the network that need to stay synchronized to stay synchronized. As an example, let's say multiple encoders. Let's say you have an application where you want to add half a dozen encoders. That's what you have in your machine, and you'd like an OCS to easily be able to interface with a half a dozen controllers. Well, for those of you who use OCS a lot, you know that we can support up to 2 encoder inputs through a hardwired connection with our high-speed counter capability. But if you need more than 2, you need to get a special high-speed coprocessor unit. Well, an alternative to that is to use network-based or CANopen-based encoders. Well, how do you keep them synchronized? You know, field buses don't work good for encoders because the data comes back non-synchronized. Well, with CANopen, it stays synchronized. How does that happen? Well, what happens is the master, in this case the OCS, sends out a sync pulse, let's say every 20 milliseconds. Every slave receives the sync pulse at exactly the same time, and those that are configured to respond to that sync pulse will use that pulse to capture, as in the case of an encoder, they could capture the current position of the encoder at the exact instant the sync pulse was received, and then it can respond to the sync pulse by responding back with that current position. Now, it doesn't really matter whose position for which encoder gets back to the master first, because the data that gets back to the master gets back quickly, and it was all captured at the exact same instant of time. So a very cool capability. Now there's actually 2 parameters that you can configure with the sync pulse, and that's done on the master side. On the OCS side, there's the communication cycle period, which is the frequency between sync pulses. So if you want to send out a sync every 20 milliseconds, the communication cycle period would be 20 milliseconds. And then it's specified in microseconds, so it's got a lot of resolution. And then you have what's called the synchronous window length, and that is the amount of time that you're going to allow anybody who is synchronized with a sync pulse to generate their PDO messages after they receive the sync pulse. So let's say I'm sending out a sync pulse every 20 milliseconds, and I want to be sure that every slave out there, let's say 6 encoders, respond within 3 milliseconds or 5 milliseconds of the time they receive that pulse. Well, I can set the synchronous window length to say 3 milliseconds, and if a slave can't respond within 3 milliseconds to that sync pulse they received with their data, then they just don't send it. And then the master can notice that, and it can take action if necessary. So again, the sync pulse is a very cool function in CANopen that makes it much better than a lot of other field bus protocols, especially CAN-based field bus protocols and less expensive field bus protocols. I mean, you can do a lot of the synchronization in higher level Ethernet protocols, you know, especially things like EtherCAT and those sorts of things, but that's a different level of complexity and pricing than what you get with a, you know, with a CANopen device often. Okay, so those are really the main highlights that I wanted to cover. I'm also going to cover, you know, some of these other protocols as well, just so you know what they are. But the real highlights, I've pretty much covered those. The PDO, the SDO, you know, what state does the network need to be in, or what state does each individual device need to be in to exchange data, and then that very cool sync protocol for keeping multiple devices synchronized. All right, now another protocol that's available is the emergency protocol. It's optional in that you don't have to utilize it. And a lot of these protocols I've talked about are kind of optional. You don't necessarily have to configure them. But I've talked about all the useful ones so far, except for node guarding, of course. But anyway, with the emergency protocol, you can set that up so that if a CAN slave, for instance, detects an internal error of some sort, it can send an emergency message out that the master will recognize and the master can take action, for instance. So that is a way of handling a exception like that. But again, it's an optional protocol that does not need to be implemented in every system for sure. Another useful in some cases, but kind of superfluous in others, is the timestamp protocol. So if you think it's very critical that you have multiple devices that all stay on the same highly synchronized time, you can utilize the timestamp protocol. Typically the way that works is the CANopen master, which is usually the OCS, is going to send out over the network a CAN message that contains this timestamp with every message, and that timestamp is going to contain the time of day, which is going to include not only the number of days since January 1984, but also the number of milliseconds today since midnight. Okay, so again, pretty rare that you'd want to use that, but it's there and available. Okay, so again, what I wanted to do with today's session, my main goal was to introduce what is CANopen, why is it useful, what are the use cases for it, and take some of the mystery or some of the intimidation factor out of using it. And again, you're not going to use it in a high percentage of applications, but if you've got a low-end motion control application, low-end from a pricing standpoint, if you have a need to add multiple encoders over CANopen or over some other network, there are some terrific use cases for CANopen. And next week, we're going to go hands-on with several of them. Okay, for the next couple minutes, I just want to show you how to select CANopen in an OCS application. So for that, I need to fire up Cscape, which I have done here. Okay, and I've got a couple of projects here that are open. Let's go ahead and start with this. Let's start with this, my currently open project, which is an XL4. So let me go to the hardware configuration here. Okay, so I've got an XL4. How do I select CANopen for an XL4? Because there is no part number, if you will, for CANopen from the factory. You just order a standard, XL4 with whatever I/O option that you want. Well, like I mentioned earlier in the presentation, you can download CANopen firmware from our Horner website, install that firmware in your XL4, and now on the CAN port, instead of it being CScan, the first CAN port is now CANopen. So you would go in and select, under CAN 1, you would select CANopen instead of CScan or J1939. All right? And then you hit the config button. Now, the first time you do this, okay, you're going to be asked to select whether you want CANopen in your application to be used as a master in the OCS or as a slave. And if you're talking about an XL4 or an XL7 or other typical products, you're almost always going to be talking about a master. Now next week, we're going to go into great detail on how to integrate, how to configure real-world CANopen slaves that are useful in various applications, integrating those with the OCS to take the mystery out of it. This week I just wanted to show you how to actually access or select CANopen if you say you had an XL4. Okay, so you just, after doing your firmware update, you select CANopen on the CAN 1 port and hit the config button. Now, what if I also have some local I/O, or I'm not local I/O, if I also have some remote I/O that I need to add to the system as well. I don't not only, let's say this is an application where I have half a dozen CANopen encoders, but I also need some remote I/O, and I'd like to use the CAN port, but I can't use CScan and CANopen on the same port. Well, you'll notice in the tab up here for remote I/O that under CAN 1, you now have an option for CANopen I/O. All right, so if I click on that tab and hit add, you'll notice a single choice, which is a SmartRail CANopen slave I/O base. Okay, So now I have, using the exact same dialog boxes that I normally use when I configure SmartRail, whether I'm talking CSCAN or whether I'm talking Ethernet, it's basically the same dialog boxes, and I can configure a base of I/O with CANopen just like I would with CSCAN. So that makes it nice and convenient. Now I don't have the options of Smart Sticks or Smart Block or some of the other, Horner I/O family. I pretty much have SmartRail as my option. But you do have the ability now to have not only CANopen devices on your network, but also Horner Remote I/O. And I'm not going to go to the process of configuring this. It just configures like every other SmartRail I/O block. Okay, so I'll hit cancel here. All right, so that is an example of how you might select CANopen on an XL4 and how you could even add Remote I/O in that same CANopen protocol. Well, what if I have an XL7 instead? All right, so let's go ahead and let me pull up my XL7 program here. Okay, and let's go back to hardware configuration. Now in the case of the XL7, I don't need to do any kind of a firmware update to the XL7 because the XL7 has 2 CAN ports, and the second port is selectable for CANopen. Now my first port, okay, you'll see a CANopen choice there, but trust me, select CSCAN on port 1 and CANopen on port 2. Now what is that CANopen option on port 1? What in the world is that? Well, we do have the ability, only with the XL7, for you to have CANopen support on both CAN1 and CAN2, but that's really rare. Much more common is CSCAN on port 1 for adding I/O, etc., and CANopen on port 2 for handling motion control or interfacing with third-party devices, whatever the case may be. Okay, so I select CANopen on CAN2, and I hit the config button. And this is the first time for this particular program that I've pressed the config button. So this is the choice you always get. Do I want to add CANopen as a master or as a slave? And almost always CANopen master is what you want. And then that gets you back to the normal dialog here where you start the process of configuring CANopen. But again, I'm going to cover that next week in plenty of detail, showing you real world examples. All right, so that is the method you would use to select CANopen for a couple of our typical products, the XL4 and the XL7. All right, I think that pretty much wraps up what I wanted to cover. So I bring in Casey Gardner. So Casey, what did I screw up this week?
Well, you may or may not have enabled my audio, so they can hear me now, so that's fine.
Yeah, the wonders of post-production. And I'm sure people are just kind of wondering, why has he changed clothes and why does he have a completely different backdrop now? Well, that's because we're currently in post-production and we're overdubbing the part of the program which had no sound. So, but we didn't have any questions last week, did we?
Nope, unfortunately. So you covered it too well.
Yeah, I did it again. All right. Next week and every week, on Tuesday at 2 o'clock, we have our weekly live streams. And next week is no different. And remember, hands-on next week. So we talked about how CANopen worked this week. Next week, we're going to show you how to use it with a Horner OCS all-in-one controller. We're going to have a variety of CANopen devices. Depending on what comes in, we borrowed some hardware for this upcoming week. Hopefully it'll all come in and we'll have lots of things to show you. But I've got a couple devices already in, so we'll definitely have something to show you hands-on for sure. Okay, and I also would like to remind you that please subscribe to our channel. Again, it doesn't cost anything. And we'll try to continue to provide you with useful content that you can always watch on replay, even if you can't see it live. So we're trying to, again, provide detailed information that you'll find useful for integrating not only Horner products, but also hopefully some information that you can take with you for all of your projects, even if it's not using a Horner product. But we all know that you should be using a Horner product on every project, or at least most of them, right? Okay, very good. So once again, thanks for joining us, and we look forward to next Tuesday where we get hands-on with CANopen. Have a great day and stay safe.